In this video, I give you a short overview about the different types of RF transmission lines. We talk about different shapes, where these are used for, and how the electromagnetic field is interacting with these. In the second part of the video, I provide some basic formula and some effects you have to consider when electromagnetic fields are interacting with these waveguides. The first type of transmission line you know from high-speed internet applications, the fiberglass waveguide. Technically, it's made for guiding light, but the basic effect is often used. We have two different materials. The core is made out of material with a very high refractive index. The cladding has a very low one. Light passes through and gets totally reflected by the cladding. This technique allows light transfer about large distances with nearly no losses. The frequency we talk about lays around 200 terahertz, but on a way lower level in RF technology, we can work with the same effect. This leads us to the next type of transmission line, the dielectric waveguide. The idea is the same. We have two different epsilon r. The high epsilon r in the waveguide material and a low one in the surrounding area. As in the fiberglass type here, the EM wave gets reflected on the border area and stays within the waveguide. Typical materials for these are low lossy, for example ceramic, Teflon or PE everyone knows. Like these cheap shot cups for example, are made out of PE. Waveguides from this material are exotic and very useful in millimeter wave or sub-millimeter wave applications, like 5 or 6G mobile communication modules. Further, there are more applications like connecting with metal-clad dielectric waveguide or even in post stems, as I found out. Dielectric transmission lines are mostly used in high-frequency applications because here the refraction effect is stronger. In a field simulation, we can see how the waves are staying within the waveguide. As material, I took a special ceramic, but with other materials, the effect stays the same. This is not the power cable for your TV as you may think. We call it a Lecher line, but its geometry reminds strongly on typical power connection lines like flat web building wire that was used when slotting wall used to be tough work back in the days. Anyways, Lecher lines are simply two basic lines of copper and are able to transmit power and RF signals at once. You find it for this purpose. Furthermore, when length of this line is in relation to wavelength, they can provide function in RF circuits, but this is a topic for another video. On the right side, a field is fed inside the Lecher line. You see how the field is moving within the dielectricum? The next type is star quad. You find this geometry mostly in measuring technology due to its robustness against distortion fields from outside. Usually you find twisted wires inside to decrease distortion impact. When an outer EM field hits the waveguide, all four conductors face the same influence. But for this video, it's more intuitive to imagine the star quad as four straight lines. The main energy is focused in the mid. Consider the additional chopper shielding surrounding the waveguide. Robustness against distortion is the focus of this design. Also, you find these waveguides nearby high power radio transmission stations. They are also robust against jammers in military context. A very common waveguide class is the rectangular one. We already talked about in my previous video. The typical shape is like this. You have a rectangular metal tube and two mounting flanges for connecting the components together. You can combine those to longer structures. The system can be supplemented by curves or crossings. This is what happens in the hollow tube itself. The waves are moving like in the simulation. The waves are not leaving the inner cavity and are reflected by the walls. When most people have contact to RF transmission, they face this waveguide type, the coaxial waveguide. You've probably connected coax cables to your TV or your internet router. In the mid, we have a good reflecting conductor. Then there is dielectricum, coated by a second layer of metal. The wave is moving through the dielectricum. The power density is high at the mid conductor and decreases in outer areas. When it comes to PCB boards and small circuits, it would be too expensive to make connection by three-dimensional transmission. Instead, you usually print two-dimensional structures. But to keep your EM wave from leaving your circuit, you have to provide a dielectricum and two shieldings where it can reflect. So you use a top and a bottom layer with reflective material. You make a sandwich and wrap your RF optimized dielectricum inside. There is a variety of different microstrip line geometries or PCB board wrapping. In the next video on transmission lines, I cover PCB waveguides and their functions. Here we see the fields that occur on the top of the standard microstrip line. The magic of transmission happens in the dielectricum layer, but we can see the waves. The last type to be presented is a circular waveguide. It is related to the rectangular one, but a bit exotic. You find them in aerospace and radar applications. They are less lossy in comparison to coaxial waveguides and can transfer higher powers. The field is reflecting like in a rectangular waveguide. Here you see the field in the hollow cavity on the tube. Sometimes this tube can be filled with gas or dielectricum. The radiation stays within the tube. This was a short overview about typical waveguides. They all have the same function like this pair of transmission lines, guiding electricity, but in a way higher frequency areas. It's always the same principle. Waves are reflected on a border, mostly metallic. To keep the waves in the waveguide, either you have perfect reflection, or your dielectricum provides a natural border where the waves are not leaving. Part 2. Let's talk about connecting these waveguides. Changes in waveguides always cause problems. For example, improperly mounted devices or sharply changing geometry. When the wave arises, a lot of it reflects on these edges.
And there is a specific physical size to describe this kind of resistance. It's the surge impedance.
Two lines have two own surge impedances, Z1, Z2. If these don't match, we get reflections. Surge impedances are dependent on occurring inductivities and capacities.
We get some uncomfortable side effects with high frequencies. For example, straight lines develop parasitic inductivities. Parallel objects develop capacity. Open endings develop effects. Groundings develop effects. Edges develop effects. Literally everything develops effects. And these effects, like parasitic capacities or inductivities, all sum up and influence your surge impedance. But this is the topic for a whole new video.